Hey, one thing just to start off with, the midterm exam, second midterm exam is on Monday in class. And with that in mind, I'm going to pull my regular Monday afternoon office hours forward to 9 to 11. So on Monday morning, 9 to 11 a.m., I'll be in Alderman Cafe to answer last minute questions prior to the exam. Okay? All right, well, back to the story here. In looking at water distribution, which we finished up last time, I made the assumption. We simplified the world. We assumed that the water flows without any rubbing effects, which we're about to reintroduce, without any turbulence, which we're about to introduce, and what else? No starting and stopping, which again we're about to introduce. So now as we enter, this is garden watering is the topic here, or it used to be hoses, faucets, and nozzles. All the things that make water and the study of liquids and gases complicated in their motion. But you can still follow it all. It's not horrible, it's complicated. Okay, with that then, today we'll introduce water's ability to rub on things, including itself, a concept known as viscosity. Starting and stopping is sort of at the end, but more importantly, what happens to water as it goes around bends, and ultimately when it loses its steady state flow and becomes turbulent. Okay, so first off, how does a faucet control flow is the question, and there are really two issues here. One is just the water has a limited amount of available energy with which it can work. I call that ordered energy. This is the energy that it has that's equivalent to work, that can actually do work, as opposed to thermal energy. Thermal energy is going to start becoming part of the story here too. And the energy that shows up in Bernoulli's equation in steady state flow, that's ordered energy. That's energy that can do work. That's not thermal energy. So when I said that water can flow through a plumbing system, this is assuming no rubbing effects. It's the energy per drop as you follow a streamline is constant. Well, it's not perfectly constant in the real world. It gradually diminishes, it decreases. Where does the energy go? It becomes thermal energy, and that's part of the story today. But okay, so in answering this question, how does a faucet control flow? It's really working with two things. One is that even in the absence of any lossy processes, set aside thermal energy problems, the water can only go so fast because it's only got so much energy per drop. And if it turns all of its available ordered energy, the energy that's equivalent to work, into kinetic energy to go as fast as it can only go so fast. And that's going to depend on who supplied the water. If the water company's pumping water, it's doing work on every gallon it delivers, and so every gallon has a certain amount of energy, and it can only go so fast. And if you make it go through a narrow opening, the amount of water you can get through the narrow opening at max speed is limited. You can't get 1 billion gallons through a tiny hole if it's only being pushed with the usual water supply pressures. It's a pure energy issue. Any questions about that idea? Turns all of its energy into kinetic. But even it can't even do that well. Why? Because as it flows through some opening, and the faucet creates an opening essentially a variable-sized opening. It can't even flow as efficiently as I've just described because it rubs. It rubs on all the plumbing. It rubs particularly in regions where it travels fast. And that effect is responsible for this, what I described toward the end of last time, this familiar effect that if you let the water come out at, just flow essentially freely through the plumbing system, it doesn't come out very fast. This water was supplied by some water company at high pressure, therefore had a lot of energy per drop, and yet at this point it's coming out pretty slowly, so there's not much kinetic energy. The pressure here is atmospheric pressure because it's exposed to the air and it's not accelerating, so it's the same pressure, it's atmospheric pressure, so no pressure potential energy to speak of, and the gravitational potential energy is not very high. We're on the second floor, but so there's a little bit of gravitational potential energy here, but really most of the energy the water company supplied is gone. Where did it go? It became thermal energy. This water is actually a little bit hotter than it was when it was pumped, neglecting trading temperatures with, the flow of heat is complicated, we'll get there. But basically, if nobody exchanged heat with it, it would have started at, I don't know, 70 degrees Fahrenheit. Here it's maybe 71. It's converted some of its some of its ordered energy into thermal energy. How did that happen? It's because it rubbed the whole way here. And this particular flow, as you see here, was a negotiation between, let's let the water go faster. If it goes faster, it rubs more, it loses energy faster, and it slows down. So there was a negotiation process that occurred here, and it settled on this particular flow rate. At this point, it's going as fast as it can without wasting so much energy, because energy is speed dependent in water. The energy waste, the rubbing effect is speed dependent. The faster the speed, the worse the rubbing gets. It's negotiated, so it's going through as fast as it can. If it went any faster, it would lose energy too fast, it would have to slow down. It's figured it out. Is that okay? Questions about that idea? It's wasted energy in order to just deliver the water as fast as it can. If I put my thumb over it and in place spray the room around, what I've done, I'll stop doing it. It gets awful wet. What I've done is I have slowed the water down in the entire delivery process. I backed it up. And the water, instead of going through as fast as it can and suffering the consequent energy loss, it's going through very slowly. In principle, I can make it go really slowly by really pinching off hard, in which case it doesn't rub very hard. The rubbing actually does decrease almost to zero. And it carries all of its ordered energy with it then. It's not losing energy as thermal energy. It makes it all the way to my thumb with most of its ordered energy intact in the three forms that I've already described: gravitational, kinetic, and pressure. At the very last moment, it goes through that narrow crack between my thumb and the hose, and that's essentially a nozzle. That causes the water to speed up because it's going from a wide opening to a very narrow opening. It has to go faster so as not to pile up. So it speeds up, and as a result of speeding up and having more kinetic energy, it has to lose pressure potential energy. So pressure plummets to atmospheric pressure. It shoots out at high speed, low pressure, and carrying with it essentially all of the energy supplied by the water company. Yeah, Dakota? When water goes through a nozzle and necks down, it has to speed up. So it does accelerate in the nozzle. So it is being pushed forward by high pressure behind it and atmospheric pressure in front of it. There's a difference in pressure. So the flow, these are all negotiations where when you first start the flow, life is complicated, but once it settles into steady state flow, it has negotiated an arrangement that works. The arrangement that works in a nozzle is it's got high pressure behind it. Imagine I'm the water going through just the narrowest neck of the nozzle and then out into the world, out of the open air. I'm being pushed forward by the pressure behind me and low pressure in front of me. So there's a big pressure difference. I'll visualize that. And as the nozzle is also necking down, so the water is speeding up. It does both of those things simultaneously. They're intertwined, and the energy along a streamline remains constant the whole time. So as the pressure drops in entering the narrowing, and then leaving, as the pressure drops, the pressure potential energy goes down, and the kinetic energy goes up exactly to balance that. And out it goes with all of its energy still intact. This is neglecting any rubbing effects, but converted from pressure in the back, kinetic in front. The acceleration occurred in the necking down part. Once you're out in the air, the pressure is constant at atmospheric pressure. Okay? Is that answering the question? What if it curves? If the water curves, then you get funny things that happen on the sides of the flow in the curve, and I'll come to that as water goes around a curve, it develops a pressure gradient. It has to, because something's got to make it bend. Is that okay? So I mean, the take-homes from this moment, this particular observation about faucets is, even in the world of no viscosity, no rubbing, the perfect fluid flow, when you make a fluid go through a narrow opening, you limit how much fluid can pass through, limited by its energy and energy per drop primarily. Is that okay? And when in real fluids that do rub, do experience viscosity issues, you don't even get that much flow. And the slowing effects that come about because of these rubbing processes involve losing ordered energy. You lose it forever. Once it's lost from, say, pressure potential, or lost from gravitational, or lost from kinetic, you don't get it back. It goes into thermal energy, and undoing the conversion of ordered energy into disordered energy is statistically unlikely. Remember that idea? You don't get it back. So once this water has slowed down, lost its energy in that open hose, it's you can't get the pressure. The pressure's gone. The kinetic energy's gone. All right? Some words about viscosity. Viscous forces appear within a liquid, or I should say a fluid, including air has this. When portions of the liquid or portions of the fluid are in relative motion, so one of them's moving with a certain velocity and the other one's moving with a different velocity, they rub on each other. I mean, you can keep on sort of subdividing layers and say, well, if you've got a chunk of water here that's going fast towards you and a chunk of water here that's not moving, there's going to be a whole series of chunks you can think of in between, layers in between, where the one that's nearest the not moving water will be mostly not moving, but not entirely, and the one that's nearest the water that's heading towards you fast will be mostly moving toward you fast. And there'll be a whole gradient in velocities in the water. And each of these sort of imagined layers of water will be rubbing on each other and wasting energy. They will be turning ordered energy into thermal energy, just like friction does. The difference between friction, sliding friction, and these viscous forces is the viscous forces get worse with speed. Sliding friction doesn't change much with speed. If you slide something across the surface slowly, it experiences a certain sliding frictional force. The table is pushing the ruler to the left with a certain frictional force. If I go twice as fast, it still pushes with the same force. It just doesn't care about speed. That's not true for viscosity. The faster you make those layers slide across one another, the worse they push on each other. All right? It's just the way it is. It has to do with the interactions between the molecules and the constituents of the fluids. They're bumping and tugging on each other, and the faster you go, the worse they bump and tug. All right. Well, a consequence of that rubbing effect, and the rubbing effect that it goes all the way through the liquid. So it's not just the liquid in contact with surfaces. It's actually the whole liquid. It creates complicated influences on flows, for example, through a hose. The water flowing through a hose has the feature that, first I should say, if there were no viscosity, if there were no rubbing effects, water would coast through hoses. So if you had a long, straight hose going from the left of the room to the right of the room, and you got the water started over there, it would coast all the way through. Inertia alone would make it go through. In the real world, that doesn't happen because the water, as it moves through, experiences viscous forces that slow it down. It's just like, it's exactly the same issue as, in the ideal world, I would get this stick moving to the right, and it would coast across the room and hit the wall. In the real world, it doesn't. To keep it moving at constant velocity, I have to keep pushing. I have to push with the same force to the right that sliding friction is exerting to the left. Okay? You have to do the same thing with water. If you want to make the water continue to move through a hose that's 30 feet long from left to right in the room, you have to push the whole way. And you have to push to the right with some force just as hard as these viscous forces are pushing to the left. How do you push? But how do you push on a liquid? I mean, with a solid, I can push with my hand. With a liquid, you have to push with pressure differences. It's the usual thing. So you need a high pressure where the water enters the hose, low pressure or lower pressure where the water exits the hose. You have a difference in pressure from start to finish that pushes the water through the hose and keeps it moving at constant velocity, for example. So if you got a hose, you've got this hose that's 30 feet long, say, and suppose it takes a certain pressure difference, 10 units of pressure difference between entry and exit to keep the water moving steadily along. What would happen if we double the pressure difference? If you double the pressure difference, so instead of 10 units higher here than there, you use 20 units higher here than there, the flow that goes along that will settle out after some negotiation again will be about twice the flow. So the flow through a hose is proportional to the pressure difference between start and finish. And these are sort of observations. You can theoretically predict that it should be like this too, but it comes out like this. So you want to send more water through a hose, use a higher pressure at the start compared to the end. All these things have, they have lots of applications. So the higher the water pressure supplied by your water company or by some pump, the more water you can get through the same hose, everything else unchanged. If you make the hose longer, if you double the length of the hose, so instead of being 30 feet long, it's 60 feet long, well, now you need, to keep the water going, you needed, in my story, it used to be 10 units of pressure difference in the 30-foot hose to make the certain water flow through. Well, if you add a second chunk of hose the same length on it, you need another 10 units of pressure difference to keep the water going in the second portion of hose. The upshot being that if you make the hose longer, you need a bigger pressure difference. To keep the same flow, if you double the length of the hose, you got to double the pressure difference, because now you got sort of basically two hoses back to back. Each one needs its pressure difference. So the flow through a hose is inversely proportional to its length. I'm building this crazy equation at the bottom with words. Don't worry about the pi and the 128. You would never guess those. Those are just, they come out of the theory. You know, pi, where did they, well, it comes from the fact that this is a circular cross-section hose. So more pressure difference, you get more flow through a hose. More hose length, you get less flow through the hose in proportion to 1 over the hose length. If you increase the syrupiness, the viscosity of the water, so instead of water, you switch to honey. Not surprisingly, you got to push a whole lot harder to get the same amount to go through. It turns out that the flow through the hose is inversely proportional to a physical quantity known as the viscosity of the water. It's a characteristic of the water itself. It depends on temperature. You've all seen that honey or maple syrup flow better when they're warm than when they're cold. You're getting the molecules, giving more thermal energy. They don't cling to each other as much. And consequently, the whole thing flows better. So in general, viscosities decrease with temperature. You lose the syrupiness. Viscosity and syrupiness are the same idea. You okay with the idea of viscosity? Or questions about it? I should also say that the water in a hose does not have to flow at the same speed at each place within the hose. On the walls of the hose, the water is essentially stopped. The theoretical understanding of fluids at surfaces, particularly liquids, is that that last layer that's in contact with the surface doesn't move. It just wets the surface and sits there. And the slowing effects that come about because of viscosity come about because that last layer of water up against the wall of the hose, we're inside the hose looking at the wall, that last layer of water then rubs against the layer of water just inside it, which making that layer of water just inside it have a terrible time moving forward. So the speed of the water right up near the walls of the hose is pretty slow. The fastest moving water in the hose is the water that's farthest from the walls, namely right at the center of the hose, running down the center line of the hose. That water can go faster because it's more oblivious. It's so far away from the motionless water on the walls that it sort of says, hey, I can go as fast as I like. Okay? So the last change you can make to the hose that affect how much water it carries is to change its diameter. If I haven't identified this carefully, I'm thinking of a cylindrical hose. If you change the shape, you make a square cross-section hose. I've never seen one, but life is going to be different, but the same stories will show up. Anyway, the point is if you have, clear, you change the length, you change the pressure difference, you change the viscosity, you get these fairly simple proportionalities or inversely proportional flows. The hose diameter is really significant. If you make the hose twice the diameter that it used to be, and you keep the same length, you keep the same pressure difference from start to finish, and you don't change the water, just keep the viscosity constant. So you just doubled the diameter of the hose. The water flow through that hose, when it negotiates and settles at constant velocity, is 16 times as large. It's hugely dependent on the diameter of the hose. And the reason for that is two things. I mean, first, as you make the hose larger, when you double its diameter, you quadruple its cross section. You go from this big around. You see me through a surface that's got it's a circle that has radius such and such. If you double the radius or double the diameter, the circle got bigger in both width and height. So there's a factor of 4 in the surface through which you're looking at me. Everybody okay with that? Factor of 4. So the hose has 4 times, if you double the diameter of the hose, you have 4 times as much room for water to go through. So it gives you a factor of 4 in the flow already. But the other thing is, when you double the diameter, you allow the water near the center to be twice as far from the walls as it was before. And that it turns out, allows that central water to go all that much faster through. And there's another factor of 4 that shows up because of getting distance from the walls of the hose and the motionless water on those walls. So you get a factor of 16 in the flow through a hose by doubling its diameter. The overall relationship between pressure difference, hose diameter, hose length, and viscosity is called PHYS law, which I can never remember how to spell. It is what it is. It's just named after PHYS. And it has hose diameter to the 4th power in it. Where does this matter? First, I can show you this effect, which we'll now look at this tank that's over here. So I've got a water tank. The energy was put in by Al earlier today by putting the water in up high here. It's going to come out of this hole down here and travel with therefore a certain pressure greater than atmospheric pressure. So the water is going to go through these little capillary pipes, tubes, driven by a pressure difference between whatever the pressure is here and atmospheric, and we'll see how much water goes through. So if I go through the widest of these capillaries, it typically gets all wet. Okay. So this is the widest capillary. I have to take let atmospheric pressure in there. So there's the water going through. Can you see it? No. There's a lot of water going through. That's a 2.4 millimeter capillary. Here is about a 1. Let's go to this one. This is a 1.0 millimeter capillary. It is smaller. Wow, now that was a demonstration of go the other way. Go to really wide and short, man, you get a lot of water through in a hurry. This is about 40% of the original diameter. So we've shrunk the diameter by a factor of about 2.5. And the flow goes down not by 2.5, not by 2.5 squared, but by 2.5 to the 4th power, which, boy, do I know that. It's about a factor of 25. Okay. The water's coming out drip, drip, drip. Can you see the drops? You can zoom in more. Drip, 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 drip. He's a drip. I'm a drip. Okay. You get the idea. Tremendous drop in the flow rate. Come back to center. Where this matters, the simplest example is if you go shopping for a hose at the home goods store, the Lowe's or something. The most common hoses that you have a choice to purchase have diameters 5/8 of an inch and 3/4 of an inch. And 5/8 of an inch and 3/4 of an inch they're so close. 5/8, 3/4 of an inch is basically 6/8. So 5/8 versus 6/8. What's the difference? It's a big difference because the flow rate, given everything else the same, you open the hose wide open, full pressures from the water company, 100-foot hose in both cases. It's water, so the viscosity doesn't change. The flow rate, though, differs by maybe a factor of 2, because it's the difference between 5/8 and 6/8 to this 4th power. So getting the 3/4 inch hose will deliver like twice as much water. Everything else the same. You okay with that? Why it ended up such a big difference? Similarly, if you want to put out a fire, you got to go to wider hoses. So a hose that's 2 or 3 or 4 inches in diameter can carry not just a few times more water than one that's 3/4 of an inch, but like 100 times, several hundred times as much water. It gets the water farther from the walls, and the water just roars through the center at much higher speed. All right? Also, you want more water through the hose, get a bigger pressure difference. So firefighters use pumps to boost the pressure at the start of the hose. So there's just a bigger pressure difference driving the water through the hose. It travels faster, double the pressure difference, you get twice as much water through per second. All right? Next issue. I've already done that one. This I already discussed, but I'll see whether you caught it or not. Water pours gently from an open hose as opposed to one that's pinched off at the end. Because why? You okay with the question? I get out of practice asking the questions, and then you can. Anyway, how many think because it receives little ordered energy from the water company, that somehow stops the flow? Nope. Okay. B, wastes ordered energy only as it leaves the hose's end. How about wastes ordered energy only as it enters the hose? How about wasted ordered energy throughout its trip? Yay! Yeah, when you let the water flow freely through the hose, it basically picks up as much speed as it can, does this negotiation. It can't go any faster because it'll lose so much ordered energy it actually won't arrive at the end. All right. This is just a restatement of that exact effect, that the faster you allow the water to flow through the plumbing, the worse it wastes its energy. And I've said my piece. These are always, I always post these so you can always go find them if I blast through ones that you wish you saw. And I did that demonstration. Okay. This is just a more careful rehashing of the idea that if I pinch off the water, pinch off the end of the hose, and slow its flow across the entire plumbing system, it's unable to waste energy the way it had intended. We're not working with a constant diameter hose anymore. We've pinched the end, and it's at the end that all the pressure drop occurs. Right when it leaves the last bit of the hose and goes between your thumb and the hose, that's where the pressure plummets. You've created essentially a nozzle. The water speeds up to squirt through that narrowing, and it converts all of its remaining pressure potential energy into kinetic energy and leaps out into atmospheric pressure air at atmospheric pressure. So anything that you're wondering about with regard to the water flow through an open hose, a pinched off hose, when your friends ask you why when your friends ask you why when you pinch the hose the water sprays so much farther and harder, you're okay with answering them? Okay. Now we're on to other things like what Dakota asked about earlier, when the water goes around a bend. So some of the most interesting things that happen with fluid flows is when the fluid isn't being allowed to go straight and steady. We've already encountered one version of that, which is when water goes through a nozzle. If you make the water neck down into a narrowing, which is actually the next view graph here, when the water is forced to neck down, it has to speed up, its pressure has to drop, and that's sort of somewhat a symmetrical process, and we'll come to it in a minute. But when water is forced to turn in a new direction, it's not so symmetrical, and it does some weird things. So this is a drawing of water. We're looking down on a hose. The hose is lying on the floor. The reason for that is, let's get gravity out of the story. If you keep the hose always at the same level, gravity isn't important. The hose supports the water against the pull of gravity, and otherwise gravity has no important effect. So you're looking down on a hose that was heading in this direction and is bending, and the hose ends up having turned 90 degrees to the right. So any questions about what we're looking at in concept? And the water enters and goes around the turn, and two weird things happen. It develops a weird pattern of pressures and a weird pattern of speeds inside the hose at that bend. And to give you a heads up on what the colors and lines mean, the lines, not surprisingly, are these streamlines I've talked about. And in looking at the water flowing through the hose, we're assuming essentially steady state flow. I'm setting aside viscosity for the moment. We're back to water in its pristine perfection. We're setting aside viscosity, and we're even going all the way back to steady state flow. So I'm back almost as though we're talking about water distribution, topics of yesterday and the day before. So the water enters the hose, and if you follow drops, you put a drop of ink right here on this where this arrow is, and you watch that drop of ink go, it will map out this streamline in black. That one special streamline, off it goes. And the same is true of a different streamline. This arrow over here, you put a drop of ink there, it'll follow its streamline. Anyway, so that's a whole sheaf of streamlines working their way through the hose. Those are the black lines. It's okay? So the streamlines move along. One weird thing that happens is the streamlines don't all maintain constant spacing. The streamlines were evenly spaced here by choice. When at the start of the hose, we just simply put drops of ink on evenly spaced parts of the streamline. Made life simple. And as those streamlines go through the system, oddly, they get more closely spaced here near the inside of the turn, at the part of the turn closest to the sort of the pivot point. There's kind of a pivot point right here where my laser pointer is, about which everything is sort of rotating around. So near the inside, close to the pivot point, the streamlines get closer together. And farther out, far from the pivot point, the streamlines get more widely spaced. Well, what does that mean? If the streamlines are getting closer together, it means the water is speeding up. How do you know that? Well, if we follow a ball-shaped blob of water that started right at this arrow, and it's perfectly spherical, and it goes through this system. If it stays the same shape, spherical the whole way, it's going to start bumping into its too close together neighbors. So the ball of water actually has to distort. It becomes long and thin, like a banana going down the water. And it stretches out as though it went through a nozzle. It has sped up and gotten thin and long. It's sort of necking down between its neighboring streamlines have pinched it inward, and it has to speed up to go through it's only allocated a narrower channel to go through, and so it has to speed up. You okay with the idea that when the streamlines get closer together, that indicates that the speed has increased? It's true. Okay, when the streamlines get farther apart, the ball of water has been allowed to spread out sideways. Its neighboring streamlines aren't pinching it as much as before, and the ball spreads out sideways, and it gets shorter. So unlike a banana, it becomes like, I don't know, pancake, going along face forward. It's slowed down and gotten wider, as though it went through a diffuser, a channel that got wider. Okay? So the fastest moving water in this story is not at the entry of the hose, the exit of the hose. It's in the middle of the turn. It's in the turn, close to the inside wall of the turn. That's the fastest moving water. The slowest moving water in the story is on the outside of the turn, where the streamlines got wide apart. Now, why did this happen? It happens in concert with a weird distribution of pressures. Pressure in my drawings is indicated by the colors of the rainbow, from red through, RGBIV, from red all the way through to violet. The farther you get along that sequence from red to violet, the higher the pressure is at any given location. So if you went in with a little pressure gauge, you would discover here on the red side of this central area, on the red side, the pressure is low. That's the R, the red side, the R part of the RGBIV. And on the violet side, the pressure's high. So at the same time that the water on the inside of the turn speeds up, its pressure decreases. And at the same time, water on the outside of the turn slows down, its pressure increases. So we've got a difference in pressure across the stream in this curve. It's high pressure on the outside, low on the inside. It's that pressure difference that pushes the water and causes it to accelerate around the curve. If you recall, what's life like for a person traveling in a circle? If I'm heading first to your right, and I'm going to pivot around the center where my hand is, right? I'll keep going. But I'm on a carousel now, right? I'm on a carousel. I'm always accelerating towards my left, toward the pivot, pushed there by a force toward the pivot. And the force could be the horse that I'm riding on in a carousel. It could be a string if it's a ball on a string. But in this case, it's liquid riding the carousel. And to push a liquid toward the center, you need a pressure difference from high pressure on the outside to low pressure on the inside. And that's the pressure difference. High pressure on the outside, low pressure on the inside. That bends the flow, causes it to accelerate around the turn. So it creates, and physicists talk about, or mathematicians too, self-consistent solutions. When you first turn on the water in the hose, everything's really complicated in this area and way beyond what I can do. So we have to sort of let the dust settle. There's a negotiation around stable effects, and they all settle out. When they all settle out, you get simultaneously all these things happen at once to work out. You get low pressure, high speed on the inside of the turn, high pressure, low speed on the outside of the turn. You get the pressure gradient you need to bend the flow around the turn. Is it okay? Or questions about that idea? So this really does show up. It shows up whenever you have a fluid making a turn. Consequences of this. Those pressure differences are real. If you go in there with a pressure gauge, you drill a hole in the pipe, in the side of the wall of the hose here, and observe in here, that really will be low pressure. The pressure can become quite low in certain circumstances. You actually can have it below atmospheric pressure. In certain cases, you can actually make a vacuum cleaner by cutting a small hole here. It would actually suck stuff into it because the pressure is lower than the surrounding pressure on the hose. The pressure on the inside of the outer part of the curve is quite high. That's where hoses typically will burst. If a hose is carrying water and it's gotten old and delicate, it's going to burst wherever the pressure is highest, because that's where the forces that it has to withstand are the worst. And that'll be on the outside of turns. And this occurs, it occurs in normal hoses. It occurs, alas, in human plumbing. I mean, here, as an aside, once in a while I bring up topics that are, trigger warnings. I don't know what I feel about trigger warnings, but I should say that once in a while I bring up a topic that will remind somebody of something that they'd rather not have experienced and rather forget. But people plumbing, as in arteries and stuff like that, tend to fail on the outsides of turns, because that's where the pressure is the highest. And so people get burst arteries, aortas bursting and stuff like that on the outside of turns, as the as the blood is trying to accelerate around the turn. The pressure surges up, it's highest on the outside, and there it goes. Okay? Any questions or thoughts? Okay. These same kind of effects, the bending processes occur in a nozzle. As this flow, here's flow heading to the right through a hose that's getting narrower. And whether it's a real nozzle that shoots out into the world or whether it just goes from a wide pipe to a narrow pipe doesn't really matter in concept. The water enters the hose all traveling, all at uniform pressure, traveling at uniform speed. All the streamlines are chosen to be equally spaced to make life simple. And we watch them. They get a little wider, more widely spaced right here. There's a little bit of slowdown here near the outside of a turn because the flow is actually bending to go through this nozzle. So you can't see it in my pressure coloration because it's not fine grained enough or something. But there's a bend inward on these outside streamlines. They're essentially going around a turn, and then they bend the other way. And throughout this entire process, the streamlines are tending to get closer together, which indicates higher speed. And the color is shifting toward the red end of the rainbow spectrum, from blue, which is sort of in the middle, to green, to yellow, orange, and to red. The pressure's plummeting. So we're getting higher speed. The speed is increasing. The pressure is decreasing. The flow's energy is going from pressure potential energy to kinetic energy. And that's life in a nozzle. Any questions about that? All right. Just to ask you, the opposite of a nozzle, I mentioned last time or previously, it's called a diffuser. And if air or water go through a diffuser, what happens to the pressure at the exit of the diffuser? How many think it's higher than higher than after the nozzle? It's a nozzle feeding a diffuser. How many think that the pressure rises in going through the diffuser? Okay. How many think that the pressure decreases going through a diffuser? How many think it's the same? Okay, it's a little bit of scattered around here. Most people are going for it goes higher. The point is that a diffuser is the opposite of a nozzle. It really is. The pressure does become higher as you go through a diffuser. It's just this whole story. I could flip this drawing backwards and reverse the arrows. If we have the fluid flowing, entering here at low pressure and high speed, and it goes through the diffuser, heading left instead of right, it will spread out like this. The streamlines will get farther apart, which indicates slowing down, and the color will shift from red into the blue, which toward the violet end of the spectrum, which is a rise in pressure. So diffusers actually do the opposite, perfectly the opposite of what nozzles do. They slow down the flow and they raise its pressure. Okay? Where I want to go now is to sort of the other interesting features of fluid flows. Let me get past what causes the hissing in a faucet, a hose, or a nozzle. So steady state flow is silent. It's perfect. Nothing is bouncing around creating noise. So the fact that you can hear water flow often is an indication that something's going on inside that flow that is not steady state flow. The two possibilities are starting and stopping the flow, which creates noise, and we'll do that in a minute. The other possibility is that the flow, just even though it's going seemingly steadily, has structure, fluctuations in its structure. It's got turbulence. So I've assumed no turbulence up to this point, which means that if you can follow streamlines and they go through the entire story, a drop of ink dropped here follows a fixed path and remains a nice drop of ink forever. That's not always true. If you go through, so in the flow that we've described up until now, which is whether it's steady state flow or even not steady state flow, it has a name known as laminar flow. And laminar flow means that you can watch nearby drops of ink. So instead of just putting one in and watching it cruise through its streamline, put several drops in an inch apart in some pattern, and watch those move through the system, and they will stay nearby. They'll work their way through, and they'll leave the system still with some nice pattern and nearness to one another. And this will occur most often in slow-moving flows that have few obstacles, and what obstacles they encounter are small, and it's particularly helped by things that keep the fluid all nice and smooth, which is higher viscosity, syrups. You get these beautiful flows, everything stays orderly. That's known as laminar flow, and you've seen it in these, particularly in slow-moving flows. If the flow gets faster, inertia becomes important, and inertia is the enemy of order in these flows, and it can rip them apart, and the consequences of that is what's known as turbulence. And in turbulent flow, that pattern of ink drops that you put in, instead of staying nice and close together, it gets ripped apart, and the drops get separated to arbitrary distances. Knowing where one is doesn't tell you anything about where the other ones are. They're all just like chaos. Actually, chaos is physics chaos is an turbulence is an example thereof of things that you lose track of where things are located. So, laminar flow, turbulent flow, they have a lot to do with how fast things are moving. There's a quantity known as Reynolds number. It's literally a number. It doesn't have, it depends on the situation, but it has no units. It's just a number. And it is the ratio of inertial influences to viscous influences. Inertial influences favor turbulence. This part of water is going to your left, this part going to right, they rip apart. So inertia is the friend of turbulence, enemy of laminar. Viscous influences are ordering. They try to keep the fluid all moving at the same velocity. You know, syrups, it's hard to pull part of a syrup one way and part of a syrup the other way. They're syrup, they glom onto each other. They want to go together. So the Reynolds number is a ratio of those two effects, inertial to viscous. And the inertia involves mass and therefore density. The obstacle length is sort of how far apart things get ripped. The bigger the obstacles, the harder it is for viscosity to keep things orderly. Speed is associated with inertial. The more speed you've got, the more inertial effects dominate. And finally, viscosity is the great orderer and tries to keep things together. So anyway, Reynolds number is really this ratio of density to obstacle length to speed divided by viscosity. And what I want to show you, and I've got one more demonstration to do after this. I'm going to do this demonstration here, or show you this story here. We're going to look down at this fluid here. You're looking at a fluid that's got a strange character that will show you its motion to some extent. And it turns out that fluids that are sort of water-like, they will remain laminar when they are moving slowly past objects about the size of your finger, or your finger is moving slowly through the fluid. It's the same idea. Whether the fluid moves past the finger or the finger moves past the fluid, if you go slowly, you get laminar flow. So the flow goes around the obstacle and sort of comes back together. Life is simple. No turbulence to speak of. If you start going faster, though, you get turbulence. And hallmarks of turbulence are vortices, swirly things, little tornadoes. You see the tornadoes in there? I've gone from low Reynolds number to high Reynolds number, where the transition, I've gone across the transition from this is viscosity winds and things are orderly. This is inertia winds and things are disorderly. So that's sort of the transition. I'll get that more carefully next time. I want to show you one more demonstration, though. Sorry. One more demonstration, so it's not to drag it out here again. Starting and stopping water flow. Water flow carries with it momentum. So when you get water moving through a pipe, you had to invest it with momentum. It's carrying the momentum with it and out the other end of the pipe. If you suddenly try to stop the flow, it has to give up its momentum, and it will transfer all its momentum to the end of the flow, and it can hit quite hard. That transfer involves high pressures, a surge in pressure where you stopped it, and that surge in pressure can push so hard that it can make sounds and break things. This is a gadget that has only water inside. Yeah, come back. Only water inside and an air pocket, a complicated air pocket above it. If I push this gadget down quickly, make it accelerate, the water will be left behind. And so the water will rise up in this container and compress the air above it. The air, when I stop accelerating the glass container down, the air pressure that is built up here will push the water back and make it overtake the bottom, and it will hit the bottom, transferring all its momentum in a jiffy. That's water. Can you hear it hit? How do you get a tap sound out of water? That's the water transferring all its momentum in a hurry. This is the commercial demonstrator. This is the you can do it yourself. It's a bottle, it's this root beer bottle, refilled with water because root beer is messy. And if I make this accelerate down, I put the cap on, so I trap air at the top. If you make this accelerate down fast enough, it will leave the water behind. The water will rise up in the bottle, compress the air up there. When the bottle stops accelerating downward, the water will be pushed toward the bottom of the bottle, will overtake it, and will break the bottom of the bottle. Don't believe me? Here we go. Come back here. Ready? So I got to do this before the weekend, because you can do this yourself. You can do this. People can do it. I mean, it's easiest if you put the cap back on to trap the air properly. You can do it with your hand. I've seen people do this barehanded. They hit it, accelerate the bottle down, the water goes up into the neck of the bottle, compresses the air there, and then the water is pressed down and overtakes the bottom of the bottle and knocks it out. You end up with donuts on your hand, but it is doable.